G'day, hi, I'm Glenn Morris from the Smart Energy Lab. I'm going to start on a series that I've been wanting to do for a long time, which is taking you through the whole process of designing a standalone power system and considering products. Now, you might notice from the blue stuff behind me, I've got a lot of Victron products here. They've actually sponsored this series, so I'm really happy to feature their products in it, but it's not exclusive to Victron. I will talk about a range of solutions, but Victron really do have the whole field covered when it comes to off-grid. Their range of products is just amazing. Now, I'm going to start with some drawings and explaining some basic system configuration and some of the considerations that you would make when designing that sort of system. So let's have a look. Now, starting up here, we're going to do a PV DC coupled battery charging system. So let's start with our solar array. So we've got a solar array here, and it's connected via an isolating switch or circuit breaker. Now, it's shown here as an overcurrent protection device. The reason for this is that when you DC couple to a battery system, there is a possibility of backfeed from the battery system. It depends a little bit on the configuration of the charge controller, but many charge controllers are actually have a series connection on one pole straight through to the battery. So here we go, we've got a battery system, and that battery system has got a DC-DC converter, what's commonly called a maximum power point tracking device. So let's take it real simple. Let's call this an approximately 12 volt battery. Now, I call it approximately 12 volts because a 12 volt battery goes through a range of voltages from discharge to fully charged, maybe absorption or even equalization if it's a flooded lead acid battery. The MPPT can do the voltage conversion, which is really important. So let's say my array is operating at approximately 33 volts. So it's at a higher voltage than my battery. And this is one of the first magic tricks that a maximum power point tracker does, is do that transition of voltage and current at extremely high efficiency. So 33 volts in at, let's say, at 10 amps, and therefore we've got 330 watts of power going through the battery. Now let's imagine the battery is operating at exactly 12 volts. So getting my calculator out here, I'm going to go, that's 330 watts of actual power. So 330 watts divided by 12. So we'll go 330 divided by 12 equals 27.5 amps. So that means we're charging that battery at 27.5 amps, even though the panels are only putting out 10 amps at a higher voltage. So that's one of the great things about maximum power point trackers, the ability to do that voltage current transformation. Of course, there is a small efficiency loss in that conversion process. Typically it's less than, it's actually, it's greater than, so let me just go back a step there. It's greater than something like 98.5% efficient. So efficiency is pretty high on charge controllers. Some of them are over 99% efficient. So I'm sort of ignoring that efficiency factor when I'm talking about the amps going into the battery. The other thing I'm considering, and this is a safety feature, is that we have a device here for overcurrent protection. Now, I've only shown a single line diagram here. It depends on whether this is an earthed array. That means functionally earthed. One of the two poles, the positive or negative, is connected to earth. But it is most common to have what's called a floating array. So unless your local regulations require you to functionally earth your array, or there is some other reasons such as cathodic protection that is done in telecommunication systems, and also there are some types of modules where it actually require functional earthing to avoid cathodic corrosion within the module. But those are pretty edge cases. Let's talk about the majority of standalone systems that will be using a floating array. So in that case, if it's a floating array, we've actually got two poles. So we've got a positive pole and a negative pole. So I'm drawing those both there. And let's call that positive and let's call that negative. Now the requirement, I'm really focusing on Australian and New Zealand standards here, is that you have galvanic isolation in terms of a switch. Basically, it's an air gap switch which disconnects the source, the PV array, from the downstream power conditioning equipment. So we often refer to in our standards PCE. Anything that modifies voltage, frequency or current is known as power conditioning equipment. So that PCE need to be isolated from the PV array. Now there's some other finer points about where that isolation occurs. So it depends on what standards you're complying with, but in Australia and New Zealand, AS NZS 5033 applies, and it says that you need to have isolation adjacent to the array, so within 3 meters of the array, and isolation adjacent to the power conditioning equipment, so within line of sight and 3 meters of the power conditioning equipment. But if they both happen to be, within 3 meters of each other, you'd only need the one switch. And they need to be ganged. So that means we've got a connection here so that they operate simultaneously. Now you can actually have isolation without overcurrent protection, but I've shown a circuit breaker, hence the little X, showing X for overload protection, and that means it can protect against reverse current flow from the battery system. So if our battery was to have a fault, it would cause current to flow. So that means we also need a means of isolation and overcurrent protection at the battery end. So I'm going to show that as well. So there we go. We've actually got 2 points of isolation and overcurrent protection. The reason that we've got two is it's likely that there's a gauge change between the battery cable size and the PV array cable size. Typically, on smaller systems, PV array cables are quite small, are not uncommonly to be, something like 4 millimeter square cable, which is pretty popular for PV arrays in Australia. But your battery cable might be determined by, hence higher current, a larger cable size. So you might have let's say you've got 10 millimeter square cable going to your battery to allow for higher current flows. And that's going to mean that the protection for that cable needs to be sized appropriately so that you can pass through the maximum current, but it's protecting that 10 millimeter cable from thermal overload. So there's your 2 points of isolation and overcurrent protection on that design. Now, what do these kind of products look like? So there's a range of products that I could put into this picture here, including the battery. Now the battery I've shown as a simple, automotive style battery, but Victron have kindly provided me with some dummy units here in the lab. So let's have a look. We've got a few over here. So what I've got here, now it's a dummy unit because it's so light, but actually this is a exact case of an AGM. So this is a 12 volt absorbed glass mat battery, typically used for RVs or automotive applications or a very small cabin or project. Now on the front of this it tells me that it's a 110 amp hour battery and it's a 12 volt nominal, and it's got 2 terminals, plus and minus. So this battery is capable of 110 amp hours of energy storage. But one of the first things you need to learn about energy storage when it comes to batteries is not all of it is usable. Some of it will actually sort of magically disappear when you go to discharge that battery, because the voltage will droop too much as the battery discharges. Now, lead acid batteries, absorbed glass mat or AGM, have been around for a long, long time. In fact, lead acid batteries are one of the oldest forms of energy storage. You could say water's been a form of energy storage for a long time, but in terms of electrical energy, since the 1800s we've had lead acid batteries. So it's a very mature technology, but it's got some shortcomings and some advantages. One of the shortcomings is the usable capacity. Now we often refer to, once again I'll draw a picture of a battery here, a battery having a certain capacity. So let's say this battery has 110 amp hours of capacity, and that's its 100% capacity. So we'll call that 100% capacity. Now that 100% capacity is not all usable if you want to get a good life out of that battery system. So often we'll have a maximum depth of discharge set in our equipment to suit that longevity of that battery. So if we call this the 50% depth of discharge, so DOD for short, depth of discharge point, this is the point at which we choose not to go below on a regular basis to maximize the life of that battery. Now I chose 50% because it's pretty common for off-grid system designs with lead-acid batteries to limit to 50% as your maximum depth of discharge. But you really do have that reserve capacity there if you needed it because of an emergency. The other thing to consider is how often you're going to cycle that battery. Now, if you want to get 1,000 or 1,500 or so cycles out of a lead-acid battery, it depends on the product. You have to check with the manufacturer. That 50% is probably a good number to go for. But if you've got an RV that you use, a recreational vehicle that you use intermittently, or a caravan, for instance, that gets used only in the holidays a few times a year, you're likely to want to use more of that capacity, even though it may shorten the life somewhat. So that's the first thing to consider when sizing storage, is the usable capacity and how that compares with the longevity of the battery. Now, there's another consideration, which is how do we work out the amount of energy that we can actually store in this thing? Now, I've talked in energy in terms of amp hours, but actually it's not the full picture. Energy is actually volts times amp hours. So we need to know what the battery voltage is. So if this is a 12-volt battery, and we multiply it by the number of amp hours, so 110 amp hours, that's going to tell us the total capacity in watt hours. So doing that right now, so 12 times 110 is 1,320 watt hours. Remember, watt hours are energy, amp hours is part of the energy equation. If I can only use 50% of that, therefore the usable amount of energy is significantly less. So let's cross that out and say usable is half that. So divide it by 2 because that's 50%. So usable is 660 watt hours usable. There we go. So there's our first thing about usable versus total capacity. But let's just swap this battery out for a different technology. Now over here, right next to it, I've got a slightly smaller, and in fact significantly physically lighter, even though it's a dummy. If it was a real one, it will be significantly lighter because this is a lithium-ion battery. Now lithium-ion are very popular because of their lightweight and energy and great energy density. So this unit is a 12 volt, 12.8 to be exact, so that's its nominal voltage, 100 amp hour. Now you might think, oh, it's smaller. 100 amp hours less than 110, because we just looked at that other battery and that was 110 amp hours. So are we being diddled with this one? Is it not as much capacity? But this one's got some advantages over lead acid. Now, lithium's really relatively new, like in the 90s. It was invented, lithium-ion batteries, or lithium batteries first, then lithium-ion, which is a safer form. And lithium-ion has become extremely popular in the last decade or so because of EV applications and on-grid hybrid. But you're talking about transportable vehicles, something small and light is a real plus too. So let's just look at the numbers on this one. This is a 100 amp hour battery. So initially you think, oh, well, it's smaller. But remember that discussion around usable capacity. So even though it only has a total capacity of 100 amp hours, so that's its 100% capacity. There we go. The usable capacity with lithium-ion is much greater. Now, this also depends on the manufacturer, what they rate it at, and also the number of cycles you get. But typically with lithium-ion, 80% maximum depth of discharge is quite common. Even some go higher, as far as 90%. So you get quite a lot more usable energy. So let's just be conservative and say we're going to use 80% of this battery's capacity. Therefore, it's a 12.8 volt battery. Now it's actually slightly higher voltage than the AGM. That's because of the cell voltages in lithium is different. So we've got 12.8 times 100 amp hours. And so that's going to give us 1,280 watt hours of total capacity. But remember, we're only going to use 80% of that. So we'll go down here is DOD max. That's our depth of discharge maximum here is 80%. And so of the usable capacity, of the total capacity, we're going to use 80% of that. So really, I'll cross that number out because that's just a notional value and work out what the usable capacity is. And here we go. So 1,280 watt hours times 0.8 will give me a usable capacity of, wait for it, 1,024 watt hours. Now, the thing here is that this battery seems like it's smaller than the AGM, but actually its usable capacity is significantly greater. Wow. So, I mean, that's one of the big advantages of lithium. There are a few other considerations in terms of compatibility with charging sources. So you need to check with the lithium battery specification whether it's suitable for the charge controller you're using. That some of them require a communication cable, some of them will work as a generic battery, but that depends on the manufacturer of that product. So there's a couple of things just about selecting a battery for a small DC charging system. What I want to cover lastly is a little bit about our regulations in Australia and New Zealand in terms of voltage levels and what you can work on. Now, this is very specific to Australia and to some extent New Zealand. Now, we've had a change in our regulations for battery storage systems. There's been a new standard published over a year ago called AS/NZS 5139. So it's for battery systems installed anywhere connected to PCE. Basically anything from 1 to 200 kilowatt hours of storage, from 12 volts to 1500 volts DC, really a huge range there. You need to comply with AS/NZS 5139. Now, this may change with time, but at the moment that's not enforced in New Zealand because New Zealand electricity regulations need to reference a standard, but they are enforced in all states and territories in Australia. Now, one of the key points about this standard is that we've introduced divisive voltage classifications, or DVCs. Now, DVCs are a way of classifying risk in terms of environment, so wet, damp, dry, and also whether it's voltage type, AC or DC, or voltage level. What we've done in the AS/NZS 5139 is rule out wet and damp environments as suitable for installing a battery system. And therefore and batteries are DC, so we can rule out the AC component. So we've got 3 categories left, and those categories are voltage levels. So the 3 categories are DVCA, which is up to 60 volts. In fact, to be very specific, is no greater than 60 volts for more than 0.2 of a second over any operating condition. And that would cover just about all nominal 48 volt lead acid batteries except for flooded ones. Flooded lead acid will often go over 60 volts under an equalization charge. But otherwise, for most lead acid and lithium nominal 48, 52 volt lithiums are all under that 60 volt mark. But once you go over 60 volts, up to 120 volts DC, you're in what's called decisive voltage classification B, or DVCB for short. DVCB and the next category, DVCC, which is over 120 volts and up to 1500 volts DC, both of those categories are deemed to be equivalent to low voltage. Now, low voltage sounds like safe, but actually low voltage in our standards in AS/NZS 3000 means basically it's licensed electrical work, it's dangerous, it's likely to be a shock hazard or even a potential electrocution hazard. So we deem that to be a high level of risk, and therefore safety is paramount. So once you go over 60 volts, you're into a category similar to installation wiring, that's LV. That means mechanical protection, insulation, isolation, and who can install it. It's licensed electrical work changes. So I guess what I'm saying here is there's been a bit of a big change in Australia, particularly with who can do what. So currently that is enforced in all states and territories and in Australia, and to some extent is best practice recommendation in New Zealand, but not enforced yet. So there you go. There's a bit of regulatory minutiae around installing batteries. So if you're under 60 volts, really you just need to be a competent person, but you should get the appropriate training and you should have the suitable skills and knowledge, because even below 60 volts there are other hazards with batteries, particularly burning and fire. You can get serious burns even from a 12 volt battery. If you have like metal parts on your body and you short circuit a battery, that's a very hazardous situation. Anyway, that's enough for today, and we'll continue this series. The link will be up here, and we'll follow this design process for a standalone power system and all its components. Thanks a lot.